February 7th, 1942. The Java Sea, southwest of Borneo. Commander Haruki Iki stood on the bridge of the Japanese destroyer Natsushio, watching his prize crew work frantically aboard the captured American vessel they'd found drifting, abandoned. The ship was the USS Houston's escort destroyer, USS Stewart, badly damaged and scuttled by her own crew in Surabaya's drydock just days earlier. But the Japanese had raised her, and now Iki's men were cataloguing everything aboard. In the ship's combat information center, a young Japanese naval engineer named Lieutenant Tadao Nakajima was staring at something that made no sense. Mounted above the bridge was a rotating antenna unlike anything in the Imperial Japanese Navy's arsenal. It was connected to a series of metal boxes filled with glowing vacuum tubes, cathode ray displays, and circuitry that seemed impossibly complex. The Americans had tried to destroy it with sledgehammers before abandoning ship, but enough remained, intact for Nakajima to understand what he was looking at. It was a radar set, and according to the technical manuals they'd recovered, it could detect aircraft at ranges exceeding 100 miles. Nakajima's hands trembled as he read the specifications again. 100 miles. The best Japanese naval radar, the Type 21 air search system, could barely manage 30 miles under ideal conditions. Most Japanese ships didn't have radar at all. The Imperial Navy had spent the 1930s perfecting optical rangefinders, training lookouts to have near superhuman visual acuity, and developing night-fighting tactics that relied on superior human perception. And the Americans had been detecting them from beyond the horizon all along. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The technical gap Nakajima was documenting that day in 1942 represented more than just a difference in equipment. It represented a fundamental misunderstanding of where modern naval warfare was heading, a misunderstanding that would cost Japan dearly in every major engagement to come. But the real tragedy wasn't that Japan lacked the technology. The tragedy was that they had possessed the fundamental science years earlier and had deliberately chosen not to develop it. The story of Japanese radar development is a case study in institutional failure, strategic blindness, and the catastrophic consequences of allowing doctrine to override technological reality. It's the story of how one navy's devotion to tradition and human superiority led them to dismiss the most important military technology of the Second World War, even after capturing working examples and examining them in detail. To understand how Japan found itself shocked by American radar in 1942, you have to understand the Imperial Japanese Navy's philosophy in the 1920s and 30s. It was a philosophy built on a single premise: quality over quantity. Japan couldn't match American industrial output, couldn't build as many ships, couldn't train as many pilots, so they would make every ship better, every pilot more skilled, every sailor more capable. This wasn't just military doctrine, it was a deeply held cultural belief that Japanese warriors possessed inherent superiority through discipline, training, and spiritual strength. The concept of seishin, spiritual power, pervaded military thinking. Proper spirit could overcome material disadvantage. Rigorous training could defeat technological superiority. The Navy poured resources into developing the world's finest optical rangefinders. By 1941, Japanese Type 94 fire control systems could accurately measure distances to targets 12 miles away, using nothing but precisely ground lenses and highly trained operators. Night battle tactics were refined through thousands of hours of training. Lookouts practiced until they could spot ships by moonlight at distances that seemed impossible. The Type 93 torpedo, known to the Allies as the Long Lance, represented this philosophy perfectly. It could travel 24 miles at 48 knots, or 12 miles at a devastating 52 knots, powered by pure oxygen that left almost no visible wake. No other navy had anything comparable. Japanese destroyer captains trained relentlessly in night torpedo attacks, learning to maneuver their ships with precision while maintaining visual contact with targets. And it worked. In the war's early months, Japanese forces achieved victory after victory. At the Battle of Savo Island in August 1942, Japanese cruisers devastated an Allied force, sinking 4 heavy cruisers in a night action that relied entirely on superior optics and training. The Americans never knew what hit them, but there was a problem with this success. It reinforced the belief that Japanese methods were superior, that technology was less important than skill and spirit. Even as evidence mounted that radar was changing naval warfare, the Japanese Navy's leadership dismissed it as a crutch for poorly trained American sailors. The deep irony is that Japan had radar technology early. In 1936, a full 6 years before Pearl Harbor, Japanese researchers successfully demonstrated radio-based distance measurement. The Naval Technical Research Institute in Yokosuka had working prototypes that could detect ships at sea. The fundamental science was sound, and the engineering was feasible. But the Navy didn't prioritize it. Funding went to perfecting optical systems instead. The researchers at Yokosuka were told that radar might be useful for navigation in poor visibility, but it couldn't replace properly trained lookouts for combat purposes. The human eye, properly trained, was considered more reliable than any electronic system. This wasn't pure technological conservatism. There were practical concerns. Early radar sets were large, heavy, and power-hungry. They required significant electrical generating capacity that many Japanese ships lacked. The vacuum tubes were fragile and required maintenance. In tropical Pacific conditions, the humidity could destroy electronic components quickly. But underlying these practical concerns was a philosophical resistance. Radar represented a democratization of capability. It meant that a poorly trained operator could achieve what previously required years of practice. It meant that American sailors, who the Japanese considered less disciplined and less skilled, could compensate for their deficiencies with technology. To many Japanese officers, this was unacceptable. It violated the fundamental principle that victory came through superior spirit and training. If warfare became about who had better electronics, Japan would lose the qualitative edge they'd spent decades developing. So while American and British researchers were pouring massive resources into radar development in the late 1930s, Japanese naval radar remained an underfunded research project. By 1941, when the Pacific War began, only a handful of Japanese ships carried any radar at all, and those systems were primitive compared to Allied equipment. The Type 21 air search radar, Japan's most advanced system at the start of the war, used a fixed antenna that couldn't determine target bearing accurately. It could tell you that aircraft were somewhere within 30 miles, but not exactly where. The Type 22 surface search radar, intended for finding ships, had even shorter range and was notoriously unreliable. Meanwhile, American destroyers were being fitted with the SC radar, which could detect aircraft at 75 miles and provide accurate bearing information. The larger SK radar on cruisers and carriers could reach beyond 100 miles. British ships carried similar systems. The Allies had taken a technology Japan had possessed in prototype form and developed it into a war-winning capability, and Japanese naval intelligence knew it. Reports from the China war zone mentioned Chinese forces that seemed to know when Japanese aircraft were approaching before they were visible. Early engagements in 1942 showed American ships changing course to evade Japanese forces before visual contact, suggesting some form of long-range detection. But these reports were dismissed or explained away. Chinese forces must have had spotters in the hills. Americans must have gotten lucky with patrol patterns. There was always an explanation that didn't require accepting that the enemy had superior technology. The capture of USS Stewart in February 1942 should have been a wake-up call. Lieutenant Nakajima's report was thorough and technically sound. He'd documented the radar's specifications, examined the circuitry, and even gotten some components working in bench tests. His conclusion was unambiguous. American radar was years ahead of Japanese systems, and this gap would prove decisive in combat. The report went up the chain of command to the Naval General Staff in Tokyo. It was read, discussed, and ultimately filed away without action. The reasoning was complex, but ultimately came down to institutional inertia and strategic assumptions. First, there was the production problem. Even if Japan wanted to copy American radar, they lacked the industrial capacity to produce it in quantity. Japanese factories were already struggling to build enough ships, aircraft, and conventional weapons. Diverting resources to a new electronic system would mean reducing output of established weapons. Second, there was the strategic calculation. Japan was winning. In early 1942, the conquest of Southeast Asia was proceeding ahead of schedule. The Navy had secured the southern resource area, captured Singapore, and pushed the Allies back across the Pacific. Why change tactics when the current approach was succeeding? Third, and perhaps most significantly, there was institutional pride. Admitting that Japanese radar was inferior meant admitting that the entire philosophy of quality through training might be flawed. It meant accepting that American industrial methods and technological focus could overcome Japanese warrior spirit. So instead of urgently developing better radar, the Navy doubled down on existing methods. More training for lookouts, better optical equipment, refined night-fighting tactics. They would beat the Americans by being better warriors, not by matching their technology, but the evidence kept accumulating. At the Battle of the Coral Sea in May 1942, American carriers detected Japanese aircraft at ranges that allowed them to scramble fighters with time to spare. At Midway in June, American forces seemed to know where Japanese carriers were before Japanese scouts had found the American fleet. After each battle, Japanese naval intelligence analyzed what had gone wrong, and each time they found reasons that didn't require acknowledging Allied radar superiority. American code-breaking explained some successes. Lucky patrol patterns explained others. Aggressive American scouting explained the rest. The institutional blindness was so complete that when Japanese submarines recovered American aircraft that had ditched at sea and found radar equipment aboard, the Naval Technical Research Institute declared it must be for navigation only. Surely the Americans wouldn't waste precious weight and power capacity putting radar on aircraft for combat purposes. By late 1942, Japan had captured or examined at least 6 different American radar systems: the SC air search radar from Stewart, the SG surface search radar from a destroyer sunk at Guadalcanal, the airborne ASB radar from a crashed torpedo bomber, the fire control radar from a downed night fighter, and components from 2 submarines. Each examination revealed the same truth. American radar was sophisticated, reliable, and devastatingly effective, and each time the institutional response was the same. Interesting technology, but not decisive. Japan would continue to rely on superior training and tactics. November 13, 1942. The waters north of Guadalcanal. Just after midnight, Rear Admiral Hiroaki Abe commanded a powerful force built around the battleships Hiei and Kirishima, supported by cruisers and destroyers. His mission was to bombard Henderson Field and destroy the American aircraft based there. But as his force approached Guadalcanal, American ships were already maneuvering to intercept. Rear Admiral Daniel Callahan's task force, built around cruisers and destroyers, had detected the Japanese ships on radar at a range of 27,000 yards over 13 miles in complete darkness. The Americans had time to prepare, time to position their forces, time to load guns and prime torpedoes. The Japanese, relying on lookouts and optical rangefinders, detected nothing until they were practically on top of the American formation. What followed was chaos. The first naval battle of Guadalcanal became a point-blank brawl in darkness, with ships passing within a few hundred yards of each other. Both sides took terrible losses. The Americans lost 2 cruisers and 4 destroyers. The Japanese lost the battleship Hiei and 2 destroyers. But the critical fact was this: the Americans chose when and where the battle occurred. They had radar. They could see the Japanese force coming and position themselves for ambush. The Japanese stumbled into an engagement they didn't know was happening until shells were already flying. Hiei, one of Japan's precious battleships, was crippled in the opening minutes by American gunfire at ranges where Japanese optical systems couldn't even acquire targets. She was finished off by American aircraft the next morning, becoming the first Japanese battleship sunk in the war. The after-action reports from Japanese survivors told a consistent story. They'd been detected and engaged before they knew the enemy was there. American ships had fired accurately in total darkness. The battle had been determined by technology, not tactics or training, and still, the institutional response was denial. The Naval General Staff concluded that Abe had been unlucky, that he'd encountered an American force by chance in a night engagement where confusion was inevitable. Better training in night combat would prevent similar outcomes. There was no fundamental examination of whether relying on optical systems against radar-equipped opponents was sustainable. The pattern would repeat at almost every subsequent engagement. The Battle of Tassafaronga in November saw Japanese destroyers win a tactical victory using their superior long-lance torpedoes, which temporarily reinforced the belief that Japanese weapons and training could overcome American technology. But it was the exception. Most engagements showed American forces detecting Japanese ships first, maneuvering for advantage, and dictating the terms of battle. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By mid-1943, the pattern was undeniable even to Japanese commanders at sea. American ships always seemed to know where they were. American aircraft found Japanese task forces with uncanny accuracy. American submarines positioned themselves along Japanese convoy routes as if they had detailed sailing schedules. Captain Tamechi Hara, one of Japan's most successful destroyer commanders, wrote in his diary after a demichment in July 1943, "The enemy detects us before we see them. They maneuver to advantage while we search blindly. Our lookouts, the finest in any navy, are rendered useless by their machines. We are fighting blind against an opponent who can see." Hara's assessment was correct. By mid-1943, virtually every American combat ship carried multiple radar systems. The newer destroyers had the SG surface search radar with 15-mile range and excellent bearing accuracy, plus the SC or SC2 air search radar, reaching 75 to 100 miles. Cruisers and battleships added the SK air search radar, with ranges exceeding 100 miles, and the Mark 8 fire control radar that could track targets and direct gunfire with mechanical precision. Japanese ships, by contrast, still relied primarily on optical systems. The few that had radar carried the Type 21 or Type 13 systems, with ranges of 30 miles at best, and those ranges were only achieved under ideal conditions. In practice, Japanese radar often failed to detect targets that American systems tracked easily. The technical gap had widened into a chasm, and that chasm was measured in ships sunk, aircraft lost, and sailors who would never come home. By 1944, Japanese engineers had examined enough captured American radar equipment to produce detailed technical assessments. What they found was sobering. The gap wasn't just in performance specifications. It was in fundamental manufacturing capability, electronic component quality, and systems integration. American radar sets used standardized vacuum tubes produced by the millions. The Western Electric 316. A tube, for example, was manufactured with tolerances measured in thousandths of an inch. These tubes could operate reliably for thousands of hours in the harsh maritime environment. Japanese vacuum tube production, focused primarily on radio receivers, couldn't match this quality or quantity. The circuit designs revealed even deeper sophistication. American engineers had developed automatic frequency control circuits that kept radar transmitters stable across temperature variations. They'd created sophisticated display systems using high-quality cathode ray tubes that showed targets clearly and tracked them automatically. The fire control radars incorporated analog computers that calculated firing solutions faster and more accurately than human operators. Lieutenant Commander Yoji Watanabe, assigned to evaluate captured American equipment at the Yokosuka Naval Technical Research Institute, wrote a report in March 1944 that laid out the scale of the problem. To match American radar capability, Japan would need to completely redesign their electronic component manufacturing, retrain thousands of technicians, divert scarce resources from aircraft and ship production, and fundamentally reorganize how electronics were integrated into naval vessels. The estimated timeline was 3 years minimum. The estimated cost was astronomical, and by March 1944, Japan was already losing the war. Watanabe's report included a particularly damning section on the American SC-2 air search radar, the standard system on destroyers. This radar operated at 100 to 1500 MHz, used a rotating antenna that provided accurate bearing information, and could detect aircraft at ranges exceeding 100 miles under good conditions. The entire system weighed approximately 500 pounds and required less than 4 kilowatts of power. Japan's best comparable system, the Type 13 air search radar, introduced in late 1942, operated at 200 MHz, used a fixed antenna array that couldn't determine bearing accurately, detected aircraft at 30 miles maximum, weighed over 1,000 pounds, and required 6 kilowatts of power. It was heavier, less capable, shorter ranged, and less reliable than equipment the Americans had been producing since 1941. But the most advanced American system, the SK air search radar fitted to carriers and battleships, represented capability Japan couldn't even attempt to replicate. Operating at 200 to 300 MHz with a rotating antenna 16 feet tall, the SK could detect aircraft at ranges exceeding 125 miles and track dozens of targets simultaneously. The SK's display system used a plan position indicator, a circular cathode ray tube that showed targets as dots on a map-like display with the ship at the center. Operators could see the entire tactical situation at a glance. Friendly aircraft returning from strikes, enemy aircraft forming up for attacks, surface ships on the horizon. It was a god's-eye view of the battlefield that Japanese commanders could only dream of. Watanabe's conclusion was stark. We are fighting a naval war with the technology of 1935 against an enemy using the technology of 1945. The gap cannot be closed during this war. Our only hope is tactical adaptation to minimize American radar advantage. But tactical adaptation had limits when the enemy could see you and you couldn't see them. June 19, 1944. The Philippine Sea, west of the Mariana Islands. Vice Admiral Jisaburo Ozawa commanded the first mobile fleet, Japan's remaining carrier strike force. His mission was to destroy the American carriers supporting the invasion of Saipan. He had 9 carriers, 5 battleships, and 473 aircraft. Opposing him was Vice Admiral Mark Mitcher's Task Force 58, with 15 carriers, 7 battleships, and 900 aircraft. But numbers alone don't tell the story. The real disparity was in detection capability. At 0600 hours, Ozawa launched his first strike wave, 69 aircraft heading toward the American fleet. The Japanese pilots believed they would achieve tactical surprise, approaching from the west with the rising sun behind them, making visual detection difficult. But TF-58's radar operators detected the incoming raid at a range of 150 miles. 150 miles. The Japanese aircraft were still an hour's flight time away, and the Americans already knew they were coming. Mitcher's fighter directors had time to scramble over 200 F-6F Hellcat fighters. They had time to position them at optimal altitude and bearing. They had time to organize them into coordinated intercept groups, and they had radar-equipped night fighters that could vector the Hellcats directly onto the Japanese formations. The Japanese strike never had a chance. American fighters tore into the formations 75 miles from the fleet. The Japanese pilots, expecting to make their bomb runs unopposed until they reached the carrier screen, found themselves in an aerial meat grinder. Of the 69 aircraft in the first wave, 42 were shot down before reaching the American fleet. Of the survivors, most were damaged and ineffective. The slaughter continued all day. Ozawa launched 4 major strike waves totaling 373 aircraft. American radar detected every single one at ranges exceeding 100 miles. Fighter directors positioned Hellcats for optimal intercepts. The coordination was devastating. By day's end, Japan had lost 315 aircraft. American losses totaled 30 aircraft, most from operational accidents rather than combat. The engagement became known as the Great Marianas Turkey Shoot, a name that captured the one-sided nature of the battle. But from the Japanese perspective, the disaster was incomprehensible. Ozawa's staff couldn't understand how American fighters were positioned perfectly to intercept every strike wave. They couldn't explain how the Americans seemed to know exactly where Japanese aircraft would be and when they would arrive. The after-action reports focused on pilot quality, training deficiencies, and tactical errors. There was minimal discussion of the fundamental problem. American radar had given the enemy complete situational awareness, while Japanese forces operated blind. Ozawa's carriers did have radar. The fleet carrier Taiho carried a Type 21 air search system, but it detected the American counterattack aircraft at only 30 miles, giving Japanese combat air patrol fighters barely 10 minutes warning. American radar had given their fighters an hour's warning. The time advantage was insurmountable. Even worse, Japanese radar couldn't track multiple targets effectively. When American aircraft attacked in coordinated waves from multiple directions, Japanese radar operators lost track of individual formations. The displays became cluttered and unreadable. Fighter directors couldn't provide useful intercept vectors because they didn't know where the attackers were. American fighter directors, using superior radar displays and practiced coordination procedures, managed dozens of fighters simultaneously, vectoring them onto specific targets with precise instructions. It was industrial-age warfare applied to aerial combat. Systematic, efficient, and utterly devastating. After the Philippine Sea disaster, Japanese naval intelligence compiled a comprehensive assessment of American radar capability based on captured equipment, technical analysis, combat reports, and interrogation of prisoners. The report, completed in August 1944, was one of the most accurate intelligence documents produced by any nation during the war. It correctly identified every major American radar system in service, accurately described their capabilities, and precisely explained how integrated radar networks gave American forces decisive tactical advantages. The report concluded that without equivalent radar capabilities, Japan could not win surface engagements, could not defend against air attacks effectively, and could not prevent American submarines from interdicting supply lines. The recommendations were equally clear. Immediately prioritize radar development. Divert industrial resources from conventional weapons to electronics production. Copy American designs, even if that meant acknowledging their superiority, and fundamentally reorganize naval tactics to account for radar disparity. The report reached Admiral Suemu Toyoda, Commander-in-Chief of the Combined Fleet, in early September. His response was to order increased training in night combat tactics and improved visual lookout procedures. The radar recommendations were noted and forwarded to the Naval Technical Research Institute for further study. This wasn't mere stubbornness. By September 1944, Japan lacked the industrial capacity to act on the recommendations, even if leadership had wanted to. American submarines had severed supply lines for critical materials. The factories that could have produced radar components were being bombed regularly. The engineering talent needed for radar development was being drafted into the army or sent to aircraft, factories desperately trying to maintain production. But there was also institutional resistance that went beyond practical constraints. Accepting that American radar was decisively superior meant accepting that Japanese doctrine had been fundamentally wrong. It meant admitting that spirit and training couldn't overcome technological disadvantage. For a military culture built on the concept of seishin, spiritual superiority, this was psychologically impossible. So the intelligence was filed, the recommendations ignored, and Japanese forces continued fighting with radar systems that were obsolete the day they were installed. October 24th to 25th, 1944. The Battle of Leyte Gulf, the largest naval engagement in history. Vice Admiral Takeo Kurita commanded the center force. 5 battleships, including the mighty Yamato and Musashi, 12 cruisers, and 15 destroyers. Their mission was to break through to Leyte Gulf and destroy the American invasion. Transports. As Kurita's force entered the Sibuyan Sea on October 24th, American carrier aircraft found them almost immediately, not by chance or lucky patrol patterns, but because radar-equipped scout aircraft had been tracking the formation since it left Brunei. The attacks began at 10:30 hours and continued all day. Wave after wave of American aircraft struck the Japanese ships. The super battleship Musashi, designed to be unsinkable, took 19 torpedo hits and 17 bomb hits over 6 hours before finally capsizing. Throughout this entire ordeal, Japanese radar provided almost no warning of incoming attacks. Musashi carried a Type 21 air search radar and a Type 13 early warning system. Both were operational, but they detected incoming aircraft at ranges of only 15 to 20 miles, giving the crew barely enough time to man battle stations before bombs were falling. There was no time to maneuver, no time to coordinate defensive fire, no time to prepare. American carriers, monitoring the battle from 100 miles away, tracked everything with SK radar. They knew exactly where Kurita's ships were, how fast they were moving, which had been damaged, and when they changed course. The task force commanders could vector aircraft to targets with precision, ensuring maximum efficiency of attack. That night, Kurita's battered force withdrew temporarily, then turned back toward Leyte Gulf for another attempt. At 0200 hours on October 25th, his ships entered the San Bernardino Strait in darkness. No American aircraft could attack at night, and Kurita believed he might achieve surprise, but American radar had been tracking him continuously. Admiral William Halsey knew exactly where Kurita was, exactly when he would emerge from the strait, and exactly what course he would take. Halsey made the controversial decision to chase the Japanese carrier force to the north, leaving only a small force of escort carriers, destroyers off Samar to face Kurita's battleships. What happened next became known as the Battle off Samar. At 0644 hours, Kurita's lookouts spotted the American escort carriers. For the Japanese, this was the first indication that enemy ships were nearby. For the Americans, radar had been tracking Kurita for hours. The escort carriers had already launched aircraft and were maneuvering away at maximum speed. The battle should have been a slaughter. 5 battleships and 12 cruisers against 6 escort carriers and 7 destroyers, but the Americans had radar, and the Japanese didn't. American destroyers made torpedo runs using radar to aim their weapons in rain squalls, where Japanese lookouts couldn't see them. American aircraft coordinated attacks using radar vectors, hitting Japanese ships from multiple directions simultaneously. Kurita, unable to determine how many American ships he was facing because his radar couldn't track targets effectively in the chaos of battle, believed he was fighting a much larger force. His ships fired at maximum range using optical fire control, wasting ammunition because they couldn't accurately determine target distances in poor visibility. After 2.5 hours, Kurita withdrew. He'd sunk 2 escort carriers and 3 destroyers, but accomplished nothing strategic. His confusion about American strength, caused primarily by lack of radar information, led him to retreat when he might have won. The entire 4-day Battle of Leyte Gulf demonstrated the same lesson repeatedly. American forces knew where Japanese ships were. Japanese forces didn't know where American ships were, and that disparity determined outcomes regardless of ship quality or crew training. Japan lost 4 carriers, 3 battleships, 10 cruisers, and 11 destroyers at Leyte Gulf. The combined fleet ceased to exist as an effective fighting force, and radar had been decisive in almost every engagement. In November 1944, with the war clearly lost, the Naval Technical Research Institute launched a crash program to produce an improved radar system. They called it the Type 22 Mod 4, and it represented Japan's last attempt to close the radar gap. The specifications were ambitious: 50-mile range for air search, rotating antenna for accurate bearing information, improved cathode ray tube display, and reduced weight compared to earlier systems. Japanese engineers worked frantically, knowing that every week without effective radar meant more ships sunk and more aircraft lost. The first prototype underwent testing in January 1945. It worked, after a fashion. Under ideal conditions with no interference, it could detect large aircraft formations at 40 miles. The display was readable, the bearing information was accurate, and the system was more reliable than earlier Japanese radar. But by January 1945, American forces had SK-2 radar with ranges exceeding 150 miles. They had sophisticated interference rejection systems. They had integrated the radar displays with plotting systems that tracked dozens of targets automatically. They had trained thousands of operators in standardized procedures. Japan's best new radar was equivalent to what the Americans had deployed in 1942. The gap hadn't closed, it had widened. Production of the Type 22 Mod 4 began in February 1945, with plans to install it on all major combatants. But American bombing had destroyed much of Japan's industrial capacity. The factories producing vacuum tubes were rubble. The precision machining shops needed for antenna construction were shuttered. Material shortages meant critical components couldn't be manufactured. By March, production had managed to complete exactly 12 radar sets. 12. The combined fleet had needed hundreds. Those 12 sets were installed on the few remaining major surface ships, where they provided marginal improvement over earlier systems, but nothing approaching parity with American equipment. The final operational deployment of Japanese naval radar came during Operation Ten-Go in April 1945. The super battleship Yamato, accompanied by a light cruiser and 8 destroyers, sortied on a one-way mission to attack American forces at Okinawa. Yamato carried 2 Type 22 Mod 4 radar sets, representing the pinnacle of Japanese radar technology. American submarines detected the force, leaving port, and radioed its position. American reconnaissance aircraft tracked it throughout the night using airborne radar. American carrier task forces positioned themselves for interception based on radar plots, showing exactly where Yamato would be and when she would arrive. On April 7th at noon, 386 American aircraft attacked. Yamato's radar detected them at 35 miles, giving the crew 20 minutes warning. It wasn't enough. The Americans struck from multiple directions in coordinated waves that overwhelmed the ship's defenses. After 2 hours of attacks, Yamato capsized and exploded, taking 2,700 sailors to the bottom. Her radar had functioned perfectly by Japanese standards. It had detected the enemy and provided warning. But American radar had controlled the entire engagement from beginning to end, tracking the Japanese force continuously, positioning aircraft optimally, and coordinating attacks with precision. The radar gap, from first detection of the force leaving port to final destruction in the East China Sea, had determined the outcome as completely as in every engagement before it. Behind the technical specifications and battle reports lay a human tragedy that statistics can't capture. Japanese sailors fought blind against an enemy who could see them clearly. They died not because they lacked courage or training, but because their leadership had dismissed technology as secondary to warrior spirit. Captain Natsushio, a destroyer squadron commander, survived the war and later wrote about the experience of fighting without radar. We trained to see in darkness, to estimate ranges by eye, to maneuver by instinct. We became excellent at these skills. But it meant nothing when the enemy detected us 50 miles away and positioned forces to ambush us before we knew they existed. We were samurai with swords, fighting an opponent with rifles. Courage was irrelevant. The psychological toll was severe. Sailors who survived engagement after engagement reported feeling helpless. They were being hunted by an enemy they couldn't see, couldn't locate, and couldn't avoid. Traditional naval tactics using weather, darkness, and terrain for concealment failed because American radar saw through all of it. Lookouts, the pride of the Imperial Navy, men who'd trained for years to spot ships at extreme ranges, found their skills worthless. They could see 10 miles on a clear day. American radar saw 100 miles in any weather. The lookouts stood their watches, knowing that by the time they spotted the enemy, the Americans had been tracking them for hours. American production workers, many of them women, had manufactured the radar sets that killed these sailors. They'd soldered circuits, tested components, and assembled systems without knowing exactly what they were building. The workers at Western Electric in New Jersey who produced SC radar sets, the engineers at General Electric in Syracuse who built SK antennas, the thousands of technicians at dozens of factories they'd won the Pacific War as surely as any admiral or pilot. Japan had the scientists who understood the principles. They had engineers capable of building radar. They had factories that could have been converted to electronics production. What they lacked was the institutional willingness to prioritize technology over tradition, to admit that American methods might be superior, to reorganize their entire military around new capabilities. That failure cost Japan dearly. Modern historians estimate that radar disparity directly contributed to 70% of Japanese naval losses after 1942. Ships that radar detected and tracked couldn't escape. Aircraft that radar vectored interceptors against couldn't penetrate defenses. Submarines whose positions radar plotted couldn't attack effectively. If Japan had matched American radar capabilities, the Pacific War would have lasted longer and cost far more Allied lives. But by 1944, even equivalent radar wouldn't have changed the outcome. American industrial superiority was too great, but it would have made the war bloodier, the battles more even, and the ultimate victory more costly. The story of Japanese radar failure is ultimately about institutional blindness and the cost of letting doctrine override evidence. It's about how organizations, whether military or civilian, can look directly at proof that their assumptions are wrong and still refuse to change course. Japan captured American radar equipment in February 1942. They examined it thoroughly. They understood exactly what they were facing, and they chose to believe that superior training and warrior spirit could compensate for technological disadvantage. That choice, repeated at every level from research institutes to the Naval General Staff, from individual ship captains to the Combined Fleet Command, determined the war's outcome as much as any battle. When one side can see the entire battlefield and the other cannot, victory becomes inevitable. The Americans understood this. They poured resources into radar development at Manhattan Project, levels of intensity and secrecy. They integrated radar into every aspect of naval operations, from fighter direction to gunnery to navigation. They trained tens of thousands of operators and technicians. They created doctrine that assumed radar would provide decisive advantages and built tactics to exploit those advantages. Japan did none of this, even after capturing proof that they needed to. The institutional resistance was too strong. The cultural commitment to human superiority over technological tools was too deep. The strategic myopia was too complete. Modern military organizations study the Japanese radar failure as a cautionary tale. It demonstrates how technological denial can doom even the most skilled and courageous forces. It shows that refusing to adapt to new capabilities, even when the evidence is overwhelming, leads to defeat. The lessons extend beyond military affairs. Any organization that dismisses technological change because it conflicts with tradition, that believes superior training can overcome fundamental capability gaps, that lets pride prevent adaptation, that organization is following the same path as the Imperial Japanese Navy. Lieutenant Nakajima, the young engineer who examined USS Stewart's radar, February 1942, survived the war. In interviews during the 1970s, he was asked why Japan didn't act on his reports about American radar superiority. His answer was simple. They didn't want to hear it. We told them the Americans could see 100 miles. They believed Japanese lookouts trained to see 10 miles were superior because they were Japanese. That belief killed thousands of our sailors. From the first captured American radar set in February 1942 to the destruction of Yamato in April 1945, Japan had over 3 years to acknowledge reality and adapt. They chose not to, and the consequence was systematic defeat in almost every major engagement. The mathematics were brutal. American radar detected targets at ranges 3 to 5 times greater than Japanese systems. This gave American forces 3 to 5 times more reaction time, allowing them to position for advantage in every encounter. When one side controls when and where battles occur, victory becomes a matter of execution rather than chance. By war's end, American industry had produced over 100,000 radar sets of various types. Japanese industry had produced fewer than 5,000, most of them inferior to American systems deployed years earlier. The production disparity matched the performance disparity, creating a compounding advantage that proved insurmountable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.